I have a disclaimer. A mistake was made for the moderate exercise section in which I described an exercise duration for moderate exercises being 20 minutes. A more realistic example would be around a 3-minute cycle. The ATP and PC stores will be used up around 10 seconds. So the lactic acid system will be required and would work for around the 3-minute mark. Furthermore, for maximum intensity exercise, instead of a 400-meter sprint, I was meant to imply that it would be more likely to be an example for one of these type of exercises would be javelin or shot put, which only requires a quick large burst of energy with the ATP system, which lasts around 10 seconds and so is most likely to suit these exercises. And if it runs out, this is when the lactic acid system may be required. Submaximal intensity and high duration exercises such as a marathon require the aerobic system. The aerobic system uses glucose from the blood or glycogen, which are found in the muscle cells, and fatty acids are usually used as a main fuel. Protein can be used as a fuel, but only tends to be used when carbohydrates and fats are very low. Oxygen is required for this system, unlike with the lactic acid store, and therefore lactic acid is not produced. The aerobic system has the ability to break down more than one type of fuel source in order to produce energy. The fuels are mainly fats, glucose, carbohydrates, and proteins. This system also relies on the circulatory system to transport oxygen to the muscles before it creates ATP in the mitochondria of muscle cells. The aerobic system could be seen as less reliable due to the fact that it relies on oxygen. However, for this reason, there is less waste products produced, so that is a positive. The time required for recovery of this system can be between a few days, a few hours, or 2 to 3 days, depending on the intensity and duration of the exercise and the level of fitness the athlete has. This graph shows that the pink line being at low intensity, therefore the fat contribution is high because it is one of the stores which are relied on when there is energy needed to be broken down. The main submaximal intensity and high duration intensity exercise examples are marathons, long distance swims, and cycles. These types of exercise have a high VO2 max. A high VO2 max is a good thing. It means that the body can take in more oxygen and deliver it to your muscles, which therefore contributes to aerobic respiration, which allows ATP to make energy for muscles contraction. Therefore, it enables you to run faster for a given effort. For this type of exercise, the typical VO2 max is around 70 milliliters at ml per kg per min, which is high. Athletes such as marathon runners may wish to measure their RER when they're training, as it tells them the amount of carbon dioxide produced in metabolism and oxygen used. It helps to indicate whether a person is burning fats or carbohydrates. If the person's RER is 7.0, then no carbohydrates are being burnt, but 100% of the fuel is fats. Being burnt is fats. This is very bad. However, when the RER is 1, then 100% of the fuel being burnt is carbohydrates and none of it is fats. This would only be good for sprinters and high-intensity athletes, as glycogen stores will be used up quickly. It's best to get a balance, and that can be inhibited by pacing yourself as a runner. A glycogen depletion can be worrying and cause fatigue because it means that the body will become more reliant on burning fat stores as they become more convenient stores to burn. In order to work aerobically, the body needs to have some glycogen stores in order to work, and if these run out, the body hits a wall, which is a term that's known for, as it is a large energy store and needs muscle contractions, and it just means that the body will have less energy and the athlete will physically not be able to go on. Athletes are recommended to pace themselves because it makes the body burn more fat stores, which run out slower than the glycogen stores. If the athlete starts too fast, then they may use their glycogen stores too fast. By pacing themselves, their fat and glycogen stores can be used at different rates, which suits the athlete in order for glycogen sparing, in order that it doesn't run out. The graph shows that there are always larger fat stores of the body because they are more easily stored than glycogen stores due to their molecular structure, and because of the lower level of glycogen, it's important that more fats stores are used. However, it is important that glycogen doesn't run out. Fat stores are important in aerobic respiration as they are present stores which can be broken down in order to make fuel for the muscles immediately. There is a high level of it present, however, if the body only uses fat stores as its only store of energy, then this is challenging for the body to metabolize fats and will physically drain the body and make it feel physically weak. It's important for the body to remain hydrated because a waste product of water can cause fatigue. It's important to hydrate following exercise to make up for the sweat you've lost. The waste products of aerobic respiration are carbon dioxide and water. At least 8 ounces of water should be needed within 30 minutes following any exercise in order to keep you hydrated, which is quite a lot. To avoid dehydration, it's not enough just to drink water during exercise. Before and after hydration are required too. In submaximal activities such as a marathon, there is a high amount of water loss, and so the body may become dehydrated as there is a longer period of time in which water can be lost. More water will be removed from the body through longer distance submaximal intensity exercise than shorter exercises because there's longer for the waste product of water to be produced. During marathons, there are water stations set up in order for the athletes to supply their body with the water in which they've lost due to the aerobic system. The cardio and respiratory system work together in order to get oxygen to the working muscles and remove carbon dioxide, which causes fatigue from the body as a waste product from muscle contraction. In submaximal intensity, long duration exercise, the muscles are forced to work for a longer amount of time, and therefore, as a result, more carbon dioxide is produced because during exercise, the muscles need more oxygen in order to contract, and they produce more carbon dioxide as a waste product. The blood picks up the carbon dioxide after it's disposed of oxygen, and it diffuses it into the plasma or it removes it out of the lungs. Calcium ions are associated with fatigue. Calcium binding to tropomyosin results in an undercover myosin binding state of actin. A lack of calcium ions prevents the development of cross bridges between actin and myosin, which leads to impaired contraction. Marathons, being an example of this type of exercise, is a long activity and therefore is more likely to be a depletion in calcium ions, and therefore the muscles fatigue quicker. Calcium ions at rest are stored in the sarcoplasmic reticulum, from which they are rapidly released upon the depolarization of the sarcolemma and the tubular membranes of the muscle cells. For muscle contraction, calcium ions are released into the cell, causing filaments in the muscle fibers to contract. So if there was a lack in calcium ions, the contractions will be less powerful. And for muscle relaxation, the calcium ions are pumped into storage, allowing the muscle filaments to relax. This slide gives a brief animation of what happens. So as you can see, number one, ATP binds to the myosin, making it detach from the actin, and then the ATP turns into ADP, which is another energy store, and it releases energy to convert myosin heads into a different state. Then the calcium binds to troponin, which exposes site on actin that myosin can grab, and then myosin then completes the power stroke, pushing the actin, and therefore the muscles can contract. Only 20% of the oxygen consumption during exercise is converted to mechanical work, whereas 80% of it ends up as heat. Most of the heat is dispatched, but at high intensities of exercise and when the environment temperature or humidity are high, there is a significant increase in body core temperature. Hypothermia refers to a group of heat-related conditions which come around by abnormally high body temperature. It is the opposite to hypothermia when the body goes abnormally cold. The condition occurs when the body's heat regulation system becomes overwhelmed by outside factors, such as high temperatures during exercise and high humidity, which prevents evaporation of water due to a layer on top of the skin, so that it can't leave the body's surface, causing a person's internal temperature to rise. The body's temperature may be over 105 Fahrenheit in order for it to be classified as hypothermia. A level of damage to the brain or other organs could happen at this temperature. Other symptoms include muscle cramps, fatigue, dizziness, headaches, nausea, vomiting, and weakness. The heart rate may get higher and the skin may get red. Pre-cooling is a technique, as you can see in to the right of the screen. This girl is wearing a ice vest. It's a technique which can be used in order to prevent hypothermia. It is the removing of the heat prior to an athletic performance. Having a lowered core temperature before and during the exercise will lower the amount of blood being shunted to the skin, therefore muscular blood flow, and therefore have beneficial effects on the athlete's performance. It may also lower the rate of water loss, as the body will have a lowered need to remove the water to cool down. This graph in the middle of the page shows one person having consumed a slushy and worn a cooling vest before the activity, compared to a control group and preheating group. And as you can see, those who pre-cooled had a much more regular heat. However, those who didn't, their temperature just increased rapidly. Cholinesterase is an enzyme that breaks down ACH after its role and prepares it to be used again. For another muscle contraction to begin, the synapse cleft has to be cleared, and when there's an excess of ACH or a lack of this molecule, the fatigue results from the inability to generate a new action potential. Acetylcholine is required to transfer the nerve impulses across the synaptic gap and initiate muscle contraction. The muscle works through the all or nothing law. If there's enough ACH, that will cause a contraction or nothing will happen. If insufficient or not enough ACH arrives at the receptor sites, then muscle contraction cannot proceed and fatigue does not occur. I meant to say fatigue does occur. In long duration exercise, a greater contribution of carbohydrate ingested in other foods will spare liver glycogen, prevent a drop in blood glucose concentration, and will help maintain the higher rate of carbohydrate oxidation necessary to sustain exercise intensity. An example of storage foods of glucose is energy gels and drinks, which the athlete can consume in order to get a high level of glucose back in the system after the loss of burning it as a fuel. Carb loading is a strategy which increases the glycogen stored in the body above its normal amount before exercise in order to make sure that there'll be enough energy stores for it. It typically involves the depletion in carbs about a week before the event in order to get the body to become aware of the